The virial equation of state is actually probably the best way we can model non-ideal gases. It has the most rigor, if you will, mathematically. However, there are other ways we can do this, and I'm going to introduce you to one of those, the van der Waals equation of state, which is actually among the oldest of these ways of modeling non-ideal gases. Now, to get into the van der Waals model, I'll simply remind you that attractive forces between molecules, so this long-range attractive interaction, this mostly affects the pressure, and it has the effect of reducing the pressure. And the repulsive forces, which are the close range or short range interactions between molecules that give it a hard sphere radius, these mostly affect the volume. So in effect, for the pressure, one way we can mathematically indicate that is to suggest that the pressure is going to have a factor that is related to the density, the molar density, times some constant. Or, in other words, this is equal to this constant divided by the molar volume squared. All right, so this is how this is a model for this, the effect of this attractive force on the pressure. For the volume, we would see that the molar volume would be affected by reducing it by the amount that is basically the molar volume of the molecules themselves. So these are the things that we're going to do to change the ideal gas model so that it reflects some of these things. And this is what is the essence of the van der Waals model. So the van der Waals equation of state would look something like this. We would construct it the same way we do the ideal gas equation of state. Basically, we would write that the effective pressure, which is going to be written this way now, with this correction factor, times the effective molar volume, which we'll write this way now, is equal to RT. So this is, if you will, this is going to be our functional form for the van der Waals equation of state, and the one that defines it for all kinds of different modeling purposes. Now, what I want to do with this is, first off the bat, to isolate the pressure on one side. Now, to do that, we would need to divide both sides by this volume minus molar volume minus its the volume of its molecules, and then we would need to subtract from both sides this correction to the force. So in other words, we could isolate the pressure here and write it as equal to these quantities, and you'll notice that as the molar volume increases, the pressure would decrease. As the molar volume decreases, the pressure would increase. So what we're after in all of this is to redefine our compressibility factor. I'll remind you that that was just equal to pressure times volume over RT. But now I'll substitute the van der Waals expression for the pressure for all of this and write this as follows. The van der Waals expression says that I'm going to have, well, I'll take V molar over RT, so the rest of this expression, multiplied by the pressure, but I'm going to use this expression over here for the pressure. So I'll have RT over molar volume minus B minus A over molar volume squared. So when I multiply this out, notice that the RTs are going to cancel here in this first term. So I'll end up with the molar volume over the molar volume minus B. Interesting juxtaposition of those terms. And then for the other term, one of the factors of molar volume will cancel here, and I'll end up with a factor that looks like this, RT times the molar volume. So this now will function as my compressibility factor when I'm looking at van der Waals gases. Now, one way we can analyze this is to say at low temperature, remember, low temperature is where attractive forces predominate. So this is where we would expect to see the following relationship. We would expect this A over RT times the molar volume to be greater than the second, well, the term that's dependent only on molar volume. All right, so when this is the case, the sign of the correction is going to be negative. All right, but what happens at high temperature? At high temperature, we'd have the opposite effect. We would have that the the effect of the attractive forces is going to be less than the effect of the finite volume of the molecules. So in this case, this is the term that predominates and the overall effect is positive. So this shows you that the van der Waals model actually does reproduce the observed behavior for the compressibility factor. I'll just draw it up here to remind you, if this is 1, compressibility factor is negative, and then it goes positive relative to the ideal gas. All right, so this is exactly what is happening here. And we can also see that at low temperature and high temperature, at high temperature we see more of an adherence, if you will, to the ideal gas equation of state. Now, the particular thing that I think is interesting about the van der Waals gas is the behavior of its isotherms. So let's see what those isotherms look like. So I'm going to draw a PV diagram. And for those isotherms, we find again that in this upper right-hand corner, they look a lot like an ideal gas, okay, as perhaps expected. They then come down, and there is an isotherm that has that interesting behavior, the separation behavior, where it goes through a zero slope, and as it turns out, a zero inflection point in the curve. So this represents something that we can call a critical isotherm. That is, it is the isotherm that sort of separates things that are strictly speaking gases from those that contain both gases and liquids. But an interesting thing happens with the van der Waals model when we go below this temperature. Instead of behaving in the way, the way real gas apparently behaves is it has a discontinuity. The van der Waals gas is continuous, but it shows this kind of oscillation in the curve, which gets more pronounced as we go higher in temperature. All right, so it's showing this interesting behavior here in the middle part, where the curve goes to a minimum, then up to a maximum, and then decays as we would expect for the high volume range of a subcritical isotherm. Now, what's going on here? And is this something we should be concerned about? Well, I want to point out that this region here corresponds to a place where the partial derivative of the pressure with respect to volume, and I'm saying partial because we're holding temperature constant, where this is positive. Now, I want you to think about what that means. That means I can increase the pressure and the volume at the same time. But in all equations of state for a gas, they usually are inversely proportional to one another. So in other words, this is a manifestly unphysical aspect of the isotherms of the van der Waals gas. And one shouldn't expect every mathematical model to immediately work out to give you everything that's physical. But here's how one might get around it, and it's a construction that is due to Maxwell. Right? For these isotherms that are below the critical isotherm, and I'll draw this coming down from the top and reaching a point over here, and then continuing more or less in the way we'd expect it to continue over on the other side. And this is the area in between where the van der Waals isotherm does not behave as expected. Van der Waals suggested a construction where we draw basically a horizontal line across here, where the area below the line and the area above the line are equal. All right, so this is the Maxwell construction. And when we do this, we can create, if you will, an isotherm and a PV diagram. I should have labeled my axes. A PV diagram for the van der Waals gas that looks a lot like the real gas isotherms, and behaves that way. And it also avoids this unphysical construction for the slope of P as a function of V. Now, I should mention there are a couple of other models like the van der Waals models called the Redlich Quang model and the Peng-Robinson that they're a little bit more complicated mathematical equations, so I haven't introduced them here, but they also show very similar features to the van der Waals, but one thing that you can say about them is they are more quantitative. That is to say, they are more accurate when it comes to comparing them with real gases. The van der Waals model isn't especially accurate, but it does capture, if you will, qualitatively the various features that we want to feature. I will say another thing about the van der Waals model, and that is that it does capture the condensation of a gas, which an ideal gas model does not do. So condensation is possible. So we see a liquid phase now emerging. And it has a critical isotherm at which the slope is equal to 0 and the second derivative is equal to 0. So the presence of a critical isotherm is another very important feature that we see in the van der Waals model. Now, an interesting aspect of this is that you can actually solve for the coordinates that correspond to this critical point in this isotherm for the van der Waals gas. And I'll simply quote the results, but these are things that are not that difficult to solve for mathematically. The critical molar volume in this case is going to be equal to 3b, where b is this parameter that appears in the van der Waals model. The critical pressure for a van der Waals gas would have the form a over 27b squared. Okay, and where the a is also this parameter that appears in the van der Waals model. Finally, the critical temperature can be found from both these and the van der Waals equation of state. So, in fact, this is not something you usually solve for directly, but you just plug in the values for the critical molar volume and the critical pressure, and you find that the critical temperature then would be given by 8A over 27B times the gas constant. All right, so these are values that one can actually find for this particular equation of state that van der Waals came up with. And we're going to exploit these a little bit in the next video to learn something more about gases that is, if you will, an intriguing property that they all have in common.